Hello students, welcome to CATCH25 Academy. Let us now start with illustrative examples of the topic circular motion. So the topic for today is circular motion. In this, let us start with illustration 37. So illustration 37 on page number 40. We are given a question in which we have a block whose mass is 1 kg. It is tied to a string of length 1 meter. So this is the diagram. So we have a string whose length is given to us as 1 meter. And we have a block which is tied to this string. So let us say at this position, we have a block which I'm showing by red color here. So this is the block. Now, in this case, the block is moved on a smooth horizontal table with a constant speed of 10 meter per second. We have to find the value of tension force. So how will we find? So first of all, we have to imagine this diagram like this. So initially we have a table. To show it in 3D, I am making a table like this. It is actually a rectangular table. And on this, we have a circular block which is moving in circular path. So this is the block which is moving in circular path. So here I have the block. This block is moving along a circle. Radius of the circular path is 1 meter. So this block is moving along a circular path like this, whose diagram we have shown here. So this is the center of circle. Now we have to find the tension in the string. So there is a string in it. I want to find the value of tension. So first of all, tension acts so as to pull. So tension will be towards the center. It will be the centripetal force. Along vertical direction, what are the forces acting on the block? One is mg, which acts downward. Another is normal reaction, which acts upward. So normal reaction upwards, mg downward. And tension is towards the center. So in this case, I can say tension acts at centripetal force. So its value is mass into centripetal acceleration. So tension is mv square by r, because the value of centripetal acceleration is v square by r. So let us substitute the value. Mass of block is 1. Velocity is given as 10. So v is 10. So v square will be 10 square upon radius is 1. So tension comes out to be 100 Newton. So this is the answer to question 37. Now let us move on to next illustration, illustration 38. So in it, we have a similar diagram. So we have a table, and on the table, we have a circular path. The radius of the circle, it is given to us as r. Now, on this, we have a circular groove. So this is the circular groove. In it, we have a mass. So this is the mass here. And it is moving in a circle. So we have a ball of mass m, which is this ball. It is moving with speed v along a smooth fixed vertical circular groove. So this is the circular groove. So here we have the table, and in between we have the circular groove. So this ball is moving in a circle. So let us think about the forces acting. So one is normal reaction, another is its weight mg. So mg force acts downward, normal reaction acts upward. Then we have the normal reaction, which will be towards center. So in this case, another force which will be in this case normal reaction of the groove of the ball. So normal reaction of the groove of the ball N2, let us say. Suppose this is N1 and this is N2. Normal reaction of the ball N2. So this is centripetal force. N2 is centripetal force because it is towards the center. So it is mv square by r. And normal reaction N1 equals mg along vertical force balance. N2 is normal reaction by the wall of the groove. Now, N is mv square by r. So our answer to this question, normal reaction, two answers. We have N1 is mg and N2 normal reaction by wall on groove is mv square by r. So these are the answers to this question. Now, next illustration, illustration 39. So in it, we have a block. So block of mass m, it is kept on the horizontal table. So suppose this is a horizontal table. And on this horizontal table, I am keeping a block. Let us show the block somewhere here. So this is the block. And we are given, this table is attached to the ground like this. Now, we have a rotation like this in circular path with angular velocity omega. Friction coefficient, it is given as mu. We have to find the value of friction force between the block and the table. So this is the table and this is our block. So we have to find the value of friction force. One force on the block is mg in downward direction, which is the weight of the block. Normal reaction is n. Now, other than that, what are the other forces? So this block is moving due to friction force. Friction force will be towards the center. It will be the centripetal force. Due to this friction force, this block will be moving in a circular path. So we can say friction is centripetal force. So we can say friction value is mv square by r. Or we can say friction is m omega square r, because omega square r is the formula for centripetal force. So the answer to this question, friction force in this case, will be equal to m omega square r. Next, let us take question number 40. In question 40, we are given a diagram. So we have a spring as shown, and this other end of spring is attached to a mass smaller. And this is moving in a circular path. Now, the mass m moves with some velocity v, which is in tangential direction. Natural length of spring is L0 initially, and spring constant or stiffness of the spring is K. We have to find the elongation in the spring. So for that, let us use spring force, which is in this direction, which is towards the center of this circular path. So we have a circular path like this, and towards the center of circular path, we have what? We have the center, and spring force in this case acts towards the center. So it is mass into centripetal acceleration mv square by r. Now, in this case, when the string is elongated, so we have the natural length L0 plus some x. So r will come out to be natural length of spring plus elongation x. So after this, spring force is kx. You know this spring force is what? Kx. And we have this spring force expression. So one is this expression, another expression is this expression. Because the LHS of two expressions is same, force of spring, we can equate the RHS. So mv square upon L0 plus x is equal to kx. So now we will get a quadratic in x. So let us cross multiply kx L0 plus kx square. So this quadratic in x will solve, and we'll get the value of x as root of whatever. So whatever we solve on quadratic. So let us solve this. Let me make some space for solving this quadratic here. So kx square plus kl0 x minus mv square equals 0. So x is minus b plus minus root of b square minus 4ac upon 2a. So this will be the value of x. So we'll take k common, and in that case, if it this will be the value. So our final answer to this question is this x value. So now moving on to our next question, which is question 41. So in question 41, we have a coin which is pushed tangentially from one angular position theta on a cylindrical surface with velocity v as shown in the figure. coefficient of friction is mu. We have to find the tangential acceleration. So let us first see the diagram. So in the diagram, we have like this. Now we have a point here. It is moved from this position theta. Radius of the circle is r. Now let us think about the forces. We have one force which is normal reaction N, another force which is mg in downward direction, and the component of mg will be mg sine theta in tangential direction. Along perpendicular direction we have mg cos theta, and friction will act in up the inclined direction or up the tangential direction. So friction in this case is mg sine theta, but friction is mu n, so mu n will be mg sine theta, but value of n in this case is mg cos theta, because if I do force balance along this direction, n will be mg cos theta. So mu mg cos theta is mg sine theta. Mg cancels and we get mu is equal to tan theta. Now this is one expression which we have. Other than that, if we think, we have one centripetal acceleration here, A. So in this case, what will be the equation along this direction? This was what we had previously, but in this case, the object is moving in circular path. So we have to account for the radial acceleration or centripetal acceleration as well. So based on that, we have big force, which is N minus mg cos theta, opposite direction, is equal to ma. So N minus mg cos theta equals ma. So N equals mg cos theta plus ma, which is v square by r. Now friction is mg sine theta, but friction formula is mu n. We'll substitute this value of n here. So mu n is equal to mg sine theta. N value will substitute here as mg cos theta plus mv square by r is equal to mg sine theta. Now m cancels on both sides. So we get mu g cos theta plus mu v square by r is equal to g sine theta. So from this, we can substitute and get the value of tangential acceleration. So tangential acceleration will be in this direction. So tangential acceleration, it is g sine theta. So based on this, we can solve this and get the value of answer. Now, after this, let us move on to our next question, which is question 42. Now, in the next question, we have a convex bridge as shown in the diagram, and we have a car here. So in this case, convex bridge has radius r. We have to find the value of normal reaction n when it is at the highest point. That highest point, what are the forces acting? Centripetal acceleration is towards the center. So equation for Newton's law will be big force minus small force is mass into acceleration. For the car, the acceleration is towards center. So big force will also be towards the center, which is mg. Minus normal reaction is small force in opposite direction, and it is equal to acceleration, which is v square by r. So n value comes out to be mg minus mv square by r. So this is the value of normal reaction. Now, if let us say we have an inverted situation in question 43. So highest point, this is the value of normal reaction. If the velocity at highest point is 0, then in that case this term will vanish and we'll have 0. So normal reaction will be mg. But if it has some velocity, so it will be mg minus mv square by r. Now question 43, we have a bridge like this in opposite direction, concave like bridge, and we have a car. So in this case, find the normal reaction at lowest point. So one force is normal reaction, another force is mg, another is centripetal acceleration AC. So big force minus small force is mass into acceleration. So in this case, for concave bridge, big force is upward force minus small force is mg is mv square by r. So n comes out to be mg plus mv square by r. This is the answer to this question. 43. Now, moving on to next question, which is question 44. In question 44, we have a situation in which we are given a car which is moving along a circular track. The mass of car is 1500 kg. Friction coefficient static is given as 0.5. We have to find the maximum value. So maximum velocity for safe turn, we already found the formula. It is, you know the formula. So in this case, we can derive the formula as well if needed. So in this case, friction force will act towards the center, and it is centripetal force, so mv square by r. We'll take the maximum value of velocity, maximum value of friction to get the maximum value of velocity. So friction maximum value is mu s n, which is mv square by r. So mu s into n, which is mg, because normal reaction is in upward direction, mg is in downward direction, they both are equal. So mv square by r, mn cancels, so we get v is root of mu rg. So v will come out to be root of 0.5 into radius. So radius of circular track, it is given as 20 meter into g is 10. So root of 100, which is 10. So the answer to this question will be 10 meter per second. Now next question 45 is of our notes. On page 45. So we have a circular track of radius 10 meter. Vehicle goes with average speed 18 km per hour, which is 18 into 5 by 18 meter per second, which is 5 meter per second. Theta we have to find out. So we'll use angle of banking formula. Tan theta is v square by rg. So phi square, which is 25 upon r into g. So 25 upon 100, which is 1 by 4. So theta is tan inverse of 1 by 4. Which is the answer to this question. In the next question, question 46, we have a civil engineer who wants to redesign a car. So in such a way that he does not want to rely on friction. So we have the velocity 10 meter per second, radius which is 20 meter, theta, angle of banking we need to find out. So same question, tan theta is v square by rg. So v is 10 meter per second, so 10 square, which is 100, upon r is 20 into g is 10, so 1 by 2. So theta will be tan inverse of 1 by 2. So this is the angle of banking which we need to have. Next, let us move on to our question 47. So in question 47, we have in this case we have a turn of radius 20 meter, velocity is 36 km per hour, which is 10 meter per second. Coefficient of static friction is 0.4, and we have to find the maximum velocity for which it does not slip down. So slipping and skidding. So two velocities we have to find out. So one is v is root of mu rg. This will be the velocity. Only friction acts. If only friction acts. V is equal to root of tan theta rg. If only banking. V is equal to root of mu plus tan theta upon 1 minus mu tan theta into rg. If we consider both friction and banking. So these are the formulas which we have already derived in the theory. So in this case, we want to first use this formula. V is equal to root of tan theta rg. So in that case, we can say tan theta is v square by rg. So v will substitute. In this case, we have to find what? The maximum velocities. So let us find the value. Maximum velocity we can get from this equation. V max is equal to root of mu plus tan theta upon 1 minus mu tan theta into rg. So root of mu, which is given to us as 0.4. plus tan theta. Tan theta we'll find from this equation. So tan theta is v square by rg. So 10 square by 20 into 10. So 1 by 2. So tan theta is 1 by 2. So 0.4 plus 0.5. 1 by 2 is 0.5 upon 1 minus 0.4 into 0.5 into rg, 20g, which is root of 200. So from this we can get the value. So we have to substitute the values. 0.9 upon 1 minus 0.4. 4 into 5 is 20. 4 by 10 into 5 by 10. 20 by 100, which comes out to be 0.2. 1 minus 0.2. So 0.9 upon 0.8 into 200. So 36. So V comes out to be, on doing the calculation, so we'll have to calculate 0.5 root. We'll have to also take the root. 0.5 plus 0.9, and we have to multiply by Rg as well. So if we multiply by Rg, so radius is given to us as 20 and G is given to us as 10. So the G will assume as 10 in this case. So in this case, we will have our answer as square root of 0.9 upon 0.8 into 200. So 9 root of 9 by 8 into 200. So let us do this calculation. So root of 9 by 8 into 200, I can write further as, so we'll have root of so we have our answer as root of 9 by 8 into 200. So if I divide by 2, this will be 4 and this will be 100. So velocity is root of 9 into 100 upon 4. Root of 9 is 3 into 10 upon 2. So velocity comes out to be 15 meter per second. So our answer to this question is 15 meter per second. So this is the velocity which we have, 15 meter per second, maximum velocity. Then if we want to have speed greater than the design speed, we will have to consider again the derivation and solve for velocity. Now, after this, let us move on next question, which we have question 48 on page number 48. So we have a concave bowl. This is a hemispherical bowl. We have a mass here. Radius here is R. mg force acts in downward direction. Normal reaction acts perpendicular direction. And we have, in this case, radius is R, it is kept vertical. This bowl is moving in angular velocity omega, like this. Now this angle here is alpha. Find the angular speed, omega. So let us think how to solve this question. One is weight mg, another is normal reaction. Let us take the components of forces. So if this angle is alpha, this angle will be alpha. So this will be mg cos alpha. This will be mg sin alpha. So normal reaction minus mg cos alpha will be equal to mass into acceleration. Why? Because we have normal reaction n, because we have mg cos alpha, and we have acceleration a. So this equation, big force minus small force, is mass into centripetal acceleration. So we have to find the value of omega in this case. So let us see n cos alpha. If I take further components, we want to find the value of omega. So from this, let's try to find. In this case, this circular path is along this direction. So if you see carefully, let me make the diagram once again. So we have question 48. So we have a hemispherical bowl. Let me make a better diagram, a bigger diagram. something like this. We have a spherical bowl and we have a mass here. And this mass is moving in this circle. Let me show it in light blue color. This mass is moving in this circle, like this. This is the center. So this is radius r. This is the center point. And suppose this radius is smaller from the center of this circle. This is smaller, let us say. So N, mg, these are the forces. Mg acts in vertically downward direction. Normal reaction acts perpendicular. Now in this case, we are given this angle, let us say as alpha. Let us take the component of this normal reaction N. Why am I taking the component of N, not the component of mg? Because we have to take the components along the direction of acceleration and perpendicular to it. This particle is moving in this circular path, blue color. So the centripetal acceleration will be like this. For the particle, centripetal acceleration is here. Normal reaction is here. Mg is like this. So take the component of normal reaction, N cos alpha. And another component which is N sin alpha. So N sin alpha in this case is equal to mv square by r, or m omega square r, because it is centripetal acceleration. So N sin alpha is towards center, so mass into centripetal acceleration. So m omega square small r. Small r is the radius of the smaller circle. Let us find the relation between small r and capital R. This angle is alpha, this is small r, this is capital R. So from this, sin alpha is opposite upon hypotenuse. So small r is capital R sin alpha. So I can substitute that value here. M omega square capital R sin alpha. Sin alpha cancel. And other than this, we have along vertical direction N cos alpha is mg. So N equals mg upon cos alpha. Substitute this value of N here. So N is m omega square r. So N is m omega square r becomes N, I can write as mg upon cos alpha is m omega square r. Mm cancels. So omega will come out to be g upon r cos alpha. So this is the value of omega. So this is the final answer to this question, root of g upon r cos alpha. So what did we do? We first of all made this free body diagram. And in this case, we have N sin alpha along center, so centripetal acceleration. So N sin alpha is mass into centripetal acceleration, which is m into omega square r. So from that, I can find the value of N. But by vertical force balance, I have N cos alpha is mg. I substitute the value of N as mg upon cos alpha in this equation. So N is omega square r. N I substitute as mg upon cos alpha and get the value of omega easily. After this, we move on to question 49. So in question 49, we have a conical pendulum. So question 49, let me draw a good conical pendulum. So this is our conical pendulum. Now, in this case, let us consider the vertical line here, the center. So this is the diagram. We have a bob of mass n. So this is the bob. Let us show it here. Its mass is m. String has length L. The velocity is tangential direction is given as v. Find the expression for v. This is an easy question. We have already done this. This angle theta, let us say. So let us make the force free body diagram. So first we have one force, which is tension force T. Another force which acts is mg. So mg and tension. Now let us say if I make a vertical line, the component of this will be in upward direction, tension component. So this angle theta by alternate angle. So this is t cos theta. And this component, the horizontal component towards center, it will be t sine theta. This is t sine theta. So t cos theta equals mg and t sine theta equals mv square by r. So r here is radius, which is this radius. This is r. This is the value r. So in this triangle we have this is r, this is L, this is theta. Now, after this, if I take these two equations and I divide them, call this 1, call this 2. So 2 divided by 1 gives us sine theta upon cos theta is tan theta, which is v square upon rg. So tan theta, which is from this triangle, if I get this side, it will be root of L square minus r square. We have to find velocity. So v is root of rg tan theta. R here I will substitute as L sine theta, because if in this triangle, if I take sine theta, it is r upon L. So small r is L sine theta. So let me substitute L sine theta into G into tan theta is sine theta upon cos theta. So velocity will be root of sine theta into root of Lg cos theta. So let us substitute the value of sine theta and cos theta. So in this case, we have to find the velocity for v, expression for v. So we already found this is the answer itself. So let us substitute v as root of L sine theta. Let us keep this sine theta upon cos theta as tan theta itself. So this will be our final answer. So final answer is velocity is root of L sine theta into G tan theta. This is the final answer. Next question, question 50. So in circular motion, we have this as the second last question in illustrative examples. So we have a small block which is connected to a massless string. So let us first make this. Let me draw the block as well. The block is, let us say, this one. And it is connected to a string like this. So let me show the string in another color. Let us say blue color. And another string somewhere here. 60 degree, that is given this. This angle is 60. This angle is also 60. So this kind of a equilateral triangle. So in this case, the small block, this block is connected to one end of two massless strings, 16 2 by 3 centimeter, with their fixed vertical rod. We have to find the angular velocity. The ratio of tension T1 upon T2, it is given to us as 4:1. This is given. Let us say this is tension T1, this is T2. 4:1. So we have to find the angular velocity. So let us first see in this case how this block will move. So let us take the components of forces. The component of this force will be T1. This angle is 30, so T1 cos 30 or T1 sin 60. And we will also have T2 sin 60 in this direction by same logic. Why? Because this angle is 30. So component of tension T1 here will be T1 cos 30, which is T1 sin 60, because cos 30 is sin 60. Similarly, T2 sin 60. So because this particle is moving in circular path like this is the circular path like this. So we can say T1 sin 60, which is towards center, plus T2 sin 60, which is also towards the center, acts as centripetal force, which is mv square by r. Okay, so this is the value. And we can also write this as m omega square r. Now let us try to find this radius in this triangle. If I make this triangle, we have an equilateral triangle, and this is the radius of circular path. This is 16 root 3 by 2. So 16 2 by 3. So this is also 16 2 by 3. So from this, let us call this form now as L. Let us call this L, and this is also L, and this is 60. This is 60. So in this right angle triangle, we can take sine 60 is R upon L. So R will be L sine 60. So I can substitute this value of R as L sine 60. So T1 sine 60 plus T2 sine 60 is equal to M omega square L sine 60. Now sine 60 cancels on both sides. We get T1 plus T2 is M omega square L. Now, after this, let us do vertical force balance. In red color, let me show vertical forces. So this component will be T1 cos 60. So this will be T2 cos 60. So from this, what I can get is, also we have the weight mg in downward direction. So we will have T1 cos 60 plus T2 cos 60 plus no. Here we will have is equal to downward force. Upward force is downward force plus mg. So this is the equation for Newton's law in vertical direction. Now we have two equations, one in horizontal, one in vertical. So we have to solve these two equations for T1 and T2. So what we'll do is I'll call this equation number 1, I'll call this equation number 2, and I'll solve these two equations for T1 and T2. And then I'll put that in this equation. T1 upon T2 is 4:1 and calculate the value of omega. So that is how we'll solve this question. Okay. So I hope you understood this concept. Equation 1, equation 2, solve for T1 and T2. And on solving, we'll get substitute the value of T1 here, T2 here, and equate it to 4/1. That will give us the value of omega. So that is how we find the value of angular velocity of the block in this case. So moving on to our last illustrative example of this circular motion, illustration 51. So in this case, we have a situation like a conical pendulum, something like this. This is the conical pendulum. Now, we also have a vertical length rod here. Let us show it in black color, something like this. And this conical pendulum is moving in circular path. Let's show the conical pendulum path like this, something like this. And in this case, we are given two wires AC. So this is wire AC, AC, and BC. So one more wire we have BC. So this is B. So we have two wires, wire 1, wire 2. They are tied to a sphere C, has mass 5 kg. So this has mass 5 kg. Horizontal circle has radius which is 1.6 meter. We have to find the minimum value of velocity V. So let us do force balance. So let us take tension T1 here, tension T2 here. And these angles are given to us as 30 and 45 respectively. So what will be the component here? So along this pink one, we will have component which is T1, let us say, and in blue one, we have tension, let us say, T2. Now, let us take the components of this T1 and T2 individually. So T2 component, what will be the component in vertical direction? So this is 45 degree here. So this angle will also be 45. So the upward component in this case will be, let us say, T1 cos 45 and T2 cos 45. And downward we have force mg, which is 5g. And along this we have one component horizontal. It will be T1 sine 30. And because this angle is 30. And another will be T2 sine 45. So along horizontal, we have equation T1 sine 30 along center plus T2 sine 45 along center is equal to mass into V square by R. Along vertical, we have T1 cos 45 plus T2 cos 45. Along, yes, so that equals mg. So in this case, along vertical, we have one force which is T1 cos 30. This angle is 30. So here also we will have, instead of this 45, we will have cos 30. So we have two equations. So I can solve these two equations. What do we need to find? We have to find the velocity value, minimum velocity. So from this, I can say that I can solve these two equations for T1. So on solving, we'll get mg minus mv square by r, where r is this radius. Radius of the circular path is r. So we will have mg minus mv square by r upon root 3 minus 1 upon 2. So this will be the value of T1. Now, this tension T1 for having circular path, it should be greater than 0. So we can say mg minus mv square by r should be greater than 0. From this, we can solve and get v is root of rg. So we can v has to be greater than root of rg. Sorry, v has to be less than root of rg. If I solve this identity, so maximum value of v will be root of rg. So this is how we'll solve this question. Tension we have already seen. Tension has to be greater than 0. So we'll solve for T1 and equate the tension to be greater than 0. So this is how we'll solve the illustrative examples of circular motion. After this, we'll start with the problem set for Newton's laws of motion with friction. So first you need to know the theory perfectly, then you need to see these problems and then start solving the unsolved problems on your own. So see you in the next session.